Okay, so we'll continue the discussion of Schur number, and we are going to talk about solving graph problems in using ASP, and talk about optimization in ASP. So this is what we saw last time, how to solve the Schur number. So basically, just to recap what we want to do, you are given two parameters. So here, the Schur number, Sk, is the largest integer n for which the interval 1 through n can be partitioned into k-some free sets. So in other words, you are given some numbers from 1 to n, and you have to divide into k subsets. Okay, so think about as putting this number from 1 to n into k different buckets. And each bucket should be so-called sum free, which means if you take numbers from there, either the same number or the two different numbers, when you add up, the addition should not be in the same bucket. So that's called sum free set. And surprisingly, this is quite a difficult problem. It's a combinatorial problem. And only S5 was known to be 160 in recent year. By using massive computing resources. Okay, so we did that last time. So actually, let's see how we can solve this problem. In fact, the problem itself can be formalized in 2 lines in the Klingo code. And you see actually multiple lines, actually 5 lines here, but all the others are comment except for the middle one. Okay. So middle one is the only one that makes sense for the Klingo. So now you should be able to understand what this is doing, right? So when you see this one, you will see that there are some symbols like n, k, and I. So n and k are placeholders, so you can assign the values in the command line. So those you can assume as just a fixed number. Now I is a variable. Is it local or global? It's global. Why? Because it has an occurrence outside this curly braces. So for the global variable, how do they ground? Expanded into multiple rules. So when I goes from 1 to n, so let's say n equals 3, then basically this will create 3 different rules where you have so I is replaced by 1, and I replaced by 2, replaced by 3. All the others are same. So let's say just k as is. So here you have this, okay, and similarly. So this is assuming that n equals 3. Okay, so let's actually do that. So let's call n equals 3 and k equals 2. Okay. Okay. So just to make it easy to write, so this is 2, this is 2, okay, and this is 1.2. Okay. So what is going on here? Now, of course, I can fully expand this. So this one simply means, let me do it one more time. So at this point, there is no variable, right? And there is only interval inside the set, and interval represents the set of values. So the first one, you can write it as 1, 1, 2, right? And you can do the same for the other things. So let me not repeat this. Okay, are we together? Okay. So what is this in doing? So let's say what we have. So in a comma b means that the first argument is a number from 1 to n, and the second number is the bucket. So in a comma b is the number a is in the bucket b. Okay. So you have numbers, and you put the numbers in the bucket. So let me actually expand this. So here you have three numbers 1, 2, 3, and you have to place those in the two bucket 1 and bucket 2. So think about, while I'm writing this, think about what should be the stable model in this case. Okay, so I'm talking about stable models of this guy. Okay, the one on the right. Okay, so maybe let me ask you a simpler question first. How many stable models are there for this program? 68. How many stable models are here?
8.
8, because you have two choices from the first one. You can choose either one in of 1, 1 or in of 1, 2, right? And same for the other two rules. So 2 times 2 times 2 is 8. So there are 8 stable models. And each of these stable models is saying that you are assigning the number from 1 to 3 to one of the values 1 and 2. What does it mean? Can you actually make it a simpler way to say? What is this talking about? It's actually counting the functions, right? So what is this thing? You're given 1, 2, 3 as a domain and 1 and 2 as the range. And how many functions can you define? Yeah, there's 8 functions, right? Are we together? You can count functions, right? So okay, let me not do these things, okay? So there are 8 functions that you can define. In other words, for each of these numbers, you can put you put exactly one. You choose exactly one bucket, right? That's a function. Okay, so you're just generating the functions here. Now, so at this point, what you say is for each of the numbers from 1 to n, you put it in one of the bucket. Now, is this bucket sum free? Not necessarily, right? You just put, so basically you just throw the numbers to the bucket. That's it, what you did, right? You just throw each number to the bucket and you're done. So in some cases you could have, so there are 2 buckets, you could have thrown 1 and 2 and maybe 3 here. Okay, so this is one possible stable model where 1 and 3 is mapped to the bucket 1 and 2 is mapped to bucket 2. This is one function. Okay. Now, if you're lucky, this is sum free, right? Each of these set is sum free. But if you're unlucky, you can have another throwing that works like this. So 1 and 2 goes to the same bucket. This is not sum free. Now, what we know so far is if you do this way, you will not actually lose the actual solution. Okay? But you may have some spurious answers, which doesn't count as sum free sets. So all you need to do is to get rid of those stable models that doesn't make sense. Okay, so you have to get out of those non-sum free sets. Okay, are we together? So basically the idea is simple. You just throw the numbers and check each of them. If they are not sum free, then forget about that assignment. Okay, so how do we do that? Any idea? You just write constraint. Constraint is our friend, right? To get rid of this, we use constraint. To generate, we use choice rules. Okay? This is actually the choice rule that we use with cardinality bound. Okay? So choice generated, but sometimes it may generate too many solutions, which you shouldn't count all of them. But you can just write one line solution here, which is this. So let me read this in English. If the number I is in the bucket S, and another number, or maybe not necessarily distinct, but some number, other number J is also in the same bucket S. Also, their sum is in the same bucket. Then this violates constraint. Okay? So if you put this number, what happens is for each bucket, if the bucket is not sum free, they will not satisfy this constraint. So those assignments will be removed. So the remaining stable models are only the good ones, where each bucket is sum free and each number is assigned to one of the bucket. Are we together? So you can just solve, you can just do this in 2 lines. How is it related to finding Schur number?
Just enumerate each number.
So Schur number, if you look at the definition was finding the largest interval. It didn't say anything about the largest interval here, but you can actually iterate this. Okay, so let's actually try that. So this is the code that you see. Okay. And how do you execute this? You just type the name of the Klingo file. Okay, you can just type Klingo if you downloaded most recent version. So you can do this, and you have to say what is the n and k. So let's try SO4. What was SO4? Do you remember? It was 44. So that means numbers from 1 to 44 can be put into 4 different buckets, and each of buckets is sum free. So let's say k. So k is the number of the bucket, right? So here it was 4, and it was 44. Okay, and the order of these things doesn't matter. So let me just type this. It's a file, the short file. Okay, and if I do that, I found the solution. Okay, so SO4 is known to be 44, but of course I didn't prove that SO4 is 44. I said SO4 is at least 44 because it's possible. So how do I say SO4 is exactly 44? How do I know that?
45 is not 7.
Try 45, and if it doesn't work, yes. So you run it, and Klingo will tell you. I don't know how long it will take. So why this is more time consuming than 44? Of course, it's a number one higher than 44, but also this time we have to make sure that there is no possibility. So you have to do exhaustive search. So that will probably take more time. Maybe let's try something simpler. Maybe SO3. So that's known to be 12, I believe. So that means 3 and 12. Okay, we got it. So it's okay. If you have 13, no, it's a found solution. Maybe it's 13. 14, no. Yeah, it is actually 13. Yeah, it is 13. So found it. Okay, so we checked. We can check that SO3 is 13. SO4, I don't know how long I try. I have to try. So, but you can try if you want. Let's see what we can do with larger number. Or maybe I could use some different tricks.
Dash T, you must rest.
Dash T is actually a good option, yes. You probably have read ahead. Okay, so let's say, let me explain. So here, this is 130. Okay, so to check whether Schur number 5 is at least 130, and let me type this one, which is to generate 4th thread so that you can do parallel processing. And let's see how long it will take. I mean, if you have more CPU than mine, but yeah, then you can try more. But I have only 4, so that's the best I can do. Okay. And of course, using the 4 CPU doesn't necessarily mean that you make 4 times faster, but there are sometimes some things that you can actually parallelize. So this will help. Okay. Okay, so as we talked about this before, Okay, so this is the command line. Okay, so this is actually the paper that shows that Schur number is 5 equals 160. Okay, I don't know how long it'll take. So maybe let's move on to the next one, and I will come back to this one. Okay, so the next problem is graph coloring. Again, for you will see many problems today. It's actually fun. It works like a magic, because to solve, you know that these problems are not trivial. On the other hand, when you write in the language of Klingon, it's typically just a few lines of the code. Okay, and maybe it's better than magic, because you can explain why it works that way, because you know what is a stable model. Okay, so you can see why this makes sense. So what is a graph coloring? So graph coloring is a typical problem, right? So you're given a graph and you have to color the node, but the two nodes are adjacent to each other, right? So what is the complexity of this problem? To existence of the coloring is an NP-complete problem. Okay, so there's no polynomial type algorithm unless P equals NP. Okay, which means that no matter what you do for the best algorithm or best data structure, whatever that you design, currently nobody could solve in polynomial time. Okay, if you can do, then there should be a breakthrough. And it has a lot of applications. Actually, most of the interesting problems in computer science are actually in this realm, or many of those problems in this realm. So for instance, a job scheduling problem. So what do we mean by this mapping from the job scheduling to the graph coloring? So the graph here, for instance, you have to assign committee members, and you have some different committees. Now the edges represent the common member, okay? Which means that this common member cannot be in two different committees at the same time, okay? So each of them should have different colors, okay? Same as you do the class scheduling. I copied from the Wikipedia, but students tell me that one of the hassle, it was an undergraduate class, and the student told me that the most complex thing is the scheduling the classes in the beginning or before the semester. You have a lot of constraint, and you cannot put this together. Okay, so physically, the same student cannot be in two different classes at the same time. So those two classes should be colored differently. Okay, so it has a lot of applications. Okay, any kind of resources that is to be shared. Okay, you cannot use the same resource for two different tasks. It can easily map into the graph coloring problems in many cases. How do we solve this? So we have to represent graph, and in terms of structure, the graph is simply just a set of vertices and set of edges. So it's actually easy to represent in this language. So here V represent the vertices. So there are actually 4 vertices, and there are edges. So basically, this 2 lines here shows that there is an edge from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 0, and 0 to 2. Now, you may interpret this as a directed edges or undirected edges. It's actually up to you. Okay? So, if you really want to have bidirectional edges, typically people write one more rule to say these are symmetric. Okay? So, let's see it. Oh, okay. So it took 121 seconds to solve that case. So we just verified that Schur number 5 is at least 130. Okay? So if you try a bit harder, you may get into 160, but I'm not going to try today. I don't have time to do that. Okay? All right. So that's the graph. Now how do we, so the graph is the instance. Okay, now you have to write the rules to find the coloring assignment. Okay? How can we do that? Okay, so first we define the set of colors. So let's just call it 1 through n. So that's just the name. We just number those colors. Okay, you can write red, green, that doesn't matter. Okay, but let me just use the numbers for denoting the color. Now, let's think about it. How do we do this coloring? In fact, it's very similar to the Schur number encoding. Okay. The first thing is the generate part. So what should we generate?
All the possible coloring to
You just assign colors to each node. So we are defining a function from colors to the node. Right? That's what you need to do. That's the generate part. Now, all this coloring doesn't satisfy the graph coloring requirement. So then you have to add constraint saying that if the two nodes are connected by an edge, then they should not have the same color. So how many more lines should I write here? Yeah, more lines, only 2. I need one generate and one test case, one constraint. So one choice rule, one constraint, that's all. So let's see. So the first is each vertex is mapped to a color. So now it should be actually familiar to you when you use this kind of construct. So what is the global variable here? X. What is the local variable? Okay. So what that means is there is each of the vertex is mapped to a color. So you're assigning. So here is a set of vertex, and there's a color, and basically you are defining a mapping. Okay. So here we use global variable to represent this domain and local variables to represent range. We are saying that so color x, I means that node x or vertex x is colored with I. Okay, are we together? So for each vertex x that you choose, you have to have exactly one color. Good. And the next thing is adjacent vertices should be of different color. Well, similar thing. So if x is colored with I, y is also colored with I, and they are connected by an edge, then this violates the constraint. So if you just add this one, then all those assignment that does not satisfy the requirement of coloring will be gone. Okay, and all the remaining are the good ones. So they are the solutions to the coloring problem. So here you see that each of the stable model is recording a solution to the given problem. So it's actually one-to-one correspondence. The stable models, the set of stable models that are generated here versus the solutions of the actual problem. Okay. So let's see if I can show the demo. But by the way, I did, yeah. So here you see the thread. There was a 4th thread, and the winner was the last one. Okay. Okay. So I think I have coloring here. Okay. So I have graph. Oh, by the way, actually I modified a bit. As you see, I don't actually even need to write colors 1, n. I can actually put inside this set. Okay, that's the same trick that you saw in the Schur number encoding. So either way is actually fine. Okay, so I have actually 2 files. One file is called color. Another file is called graph. And you can actually call Klingo on multiple files. So you just need to say those files, color and graph. And let's see, I have only placeholder that I have is the number of colors. Okay, so remember this graph. Okay, I don't know whether you can find it out. Let's actually go back to what is solution for this one? How many colors do we need? Smallest number of colors do we need to color this graph? 2. 2? 4? Okay, somebody says 2. So can you say, let's use, maybe numbers are too complex. So let's say use red and green, okay? So let me use different color here. Oops. Why can I not show? All right. Okay. Okay, what should I do? So suppose this is red. This should be green. Then I have no choice. I have to use red. But then violates constraint. So 2 coloring does not work. How about 3? Okay. So if I have R here, I can use green. I can use, I have to use this for now. What should I use here? Red. Then I can use green. So 3 coloring is possible. Okay. How many possibilities are there for 3 coloring? Well, let's check. So n equals 2 in this case is unsatisfiable, as we just checked. If you have 3, but let's try to generate all solutions. There are actually 18 possible solutions. Okay. So many of them are actually permutation. Okay? Are we together? Okay. So we are done with the coloring. Let's go to the clique. Okay, anyone knows the definition of clique? No? It's a complete subgraph, yeah. So it should be, so if the clique is a set of vertices where all the vertices are connected to each other. Okay? So as you see, so clique in a graph is a set of pairwise adjacent vertices. So which means that they should be all connected. So as you see that this is a clique, right? Because this node, okay, are all connected. So if you pick any 2 vertices from this set, they are connected. Similarly for this and similar for this. Now obviously if you have smaller cliques, that's easy to find, because if you have just 2 vertices, it's basically you just need 1 edge to connect, right? If you have 3 nodes, you just need 3 edges to connect, right? Now the more difficult part is when you have more and more vertices, it becomes more and more difficult to make a clique. Okay, so think about social network. So you have a group of people that everybody knows each other. Okay, that set cannot be too large. Okay, so many of the computer science problem is also about this clique. How do we find the clique? So we want to write answer set program such that it is a one-to-one correspondence with the cliques of the cardinality greater than or equal to n. So we are given some parameter n. So can we have a clique of size 3? Can we have a clique of size 4? It's similar to Schur number. If you increase those numbers, you can find the maximal clique. Okay? How many lines do we need? 2. Why? Think about this way. So your next homework, after maybe when you even do this current homework 3, you have to do the programming in Klingo, right? Then there will be one more set of homework that uses Klingo. So try to understand what is going on here today. So still there are 2 lines needed, which means that one is generate part, another is test part. So what should we generate here? What should we generate?
All possible subset of vertices. All possible subset of vertices.
Aha, so just choose any subset. Okay, what should we eliminate?
The subset base is not connected.
Subset that is not connected. Okay, that's it, right? So choose at least n vertices. How do we choose it? This time, we are not doing the mapping of functions. We are just choosing some values. Okay? And here, we assume that the graph was given as in the previous file, so there is a v of x and edge of xy. Now this x is a global variable or local variable? Local variable. So when it is grounded, it will generate multiple instances of in of 0, in of 1, in of 2, and so on, right? And you're selecting how many? N. Okay, so n is just a fixed number, so you can say n equals 3. That means choose 3 vertices that belongs to in predicate. Okay, so this one is actually same as saying choose a subset of V, and this subset is named in, okay, whose cardinality is greater than or equal to n. This is what this line is saying. Okay, so choose a subset of V that belongs to this in predicate, and the cardinality of that in relation should be at least n. So you just select n vertices, but they may not necessarily be connected. So you have to write one constraint. There must be an edge between the two, between those vertices is in the in predicate. Okay, let me say again. So there must, if you have a node that belongs to this in predicate, okay, these nodes must be connected. And that can be written in this way. Suppose x is in the predicate, x and y are vertices. So two vertices, or two different vertices x and y, okay, that belongs to the in predicate, but there is no edge from x to y or y to x, then this violates the constraint. Okay? Done. Okay? Any question up to this part? Alright, so okay, then let's move on. Hamiltonian circuit. What is Hamiltonian circuit?
You start from some node, then you can cover all the nodes and return to the.
Yeah, you have to go through all these vertices and has to come back to the original place, but also you shouldn't revisit the same vertex again. That's the Hamiltonian circuit. So what is the path here? So let's see whether we can actually visit all these vertices. Let's work from here. So you can tell me whether to go to the left or right or up or down. Okay, I'm working like a robot and you can just direct me to what to do. So let's start from here. Down. Right.
Keep going right.
Right.
Yep. Right again.
Right.
Then going down.
Down.
Step.
Left.
Yep. Up.
Up.
Yep. Left side.
Left. Left or right? Tell me.
Right.
Right.
Down.
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 Right.
Right.
Up.
Up.
Left.
Left.
Up.
Up. Left. Up.
Left.
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 Up.
Up. Wow. So we found it. Good. Okay, so this was actually the solution that is also given here. Yeah. All right, so we are going to solve this one. Let's actually try one more thing. It happened to be the different graph. Okay. What about this one? So let's start with one. Other than Pema. Somebody else. Right. Okay, so right. You can now give the numbers. So I'm in number 1. So 2, okay? 5,
5,
6,
3,
3, 4, 1. Okay, that's good. How many solutions will there be? That's harder, right? You can find one easily, but how many? They have to count everything. Okay. All right. So we are going to solve this problem, and obviously now you can encode this graph in the language of Klingo. Here we actually use this pooling just to make it a bit more succinct. If you don't like, that's fine. You can just enumerate edge of 1, 2, 1, 3, 1, 4. Doesn't matter. Okay? So I mean here that means that there is an edge. Okay, I have to delete this. It's too complex to read. Oh. For some reason my pen is not working. Okay. Okay, if you read this carefully, the edges are not necessarily bidirectional. Okay, so some are, but if you look at a pair between, say, 4 and 5, there's no edge from 4 to 5. There's an edge from 5 to 4, but not the other way around. Okay, so this is a directed graph that we are looking at. Okay. All right, so how do we solve this problem? Now, let's guess. How many lines do we need? This is probably more than before. That's a hint. 5 is the answer if you have previous direction note. Okay. Yes, 5. So first, think about this as you have to turn this into more precise language. So Hamiltonian circuit in a graph G is a subgraph C that has the same set of vertices as G and satisfy the two conditions. Every vertex is adjacent. Every vertex is adjacent in C to exactly 2 vertices. Okay, because it's a path. If you pick any node, there is exactly 1 incoming edge and 1 outgoing edge. Okay. That's one hint. Another thing is every vertex is reachable in C from some fixed vertex. You can just choose any vertex, doesn't matter. But you have to choose one. And from this, you can visit all the vertices. And that's it. Okay? So if you satisfy this requirement, you will see that there is no case that the same vertex is revisited twice, because if it is revisited twice, then it's doesn't have this 1 incoming edge, 1 outgoing edge. You may have 2 incoming edges, right? So that case is gone. So you just need to focus on this. So your first step is try to write in a precise statement that you can formalize in the language of Klingo. Okay? Turn your English description, whatever the Hamiltonian circuit problem that you know, turn it into more crispy and something that you can formalize in logical language. That's the first step to do. And after you do that, this is exercise. So there should be some generate part. Okay, so we're going to use choice rules. There will be also the test part, which is to use constraint. But this particular program actually has one more component, which is so-called define part. Okay, so there are actually 3 sections. Let's actually look at the generate part. What should we generate? We should generate something here, right? What is the thing that we are generating? You have to choose what? Choose edges, right? So just choose any subset of the edges. Okay? If you're lucky, that's already Hamiltonian circuit. If you're unlucky, most of the time it doesn't satisfy the requirement. Do you understand? Okay? Just given a graph, just choose randomly the set of edges. And if the set of edges are perfectly connected to satisfy the Hamiltonian circuit requirement, you're done. Okay? So, how do we do? We're going to use these 2 rules. Okay, now you can read. Here, x and, so first rule, x is a global variable, and y is a local variable. So each node x, choose particular x. Okay? Now let's actually understand this xy as an edge from x to y. This is a directed edge. Okay? So choose x, and you have to generate exactly one predicate called cycle x comma y, where y is actually a local variable. So what does it mean intuitively? Given an x, you have to choose exactly one outgoing edge, right? So if you look at this, so try to ground the global variable first. So it's a particular x, okay? It could be some node 1 or node 2. Now this y is a local variable, so it will expand the set inside. So I can say, for example, this rule will this rule will make like, let's say, 1 comma 1. Okay, what was the actually 1 comma 2? If you look at the previous one, edge 1 was connected to 2, 3, 4. Okay, so I can write okay. So when x equals 1, okay, when x equals 1, y can be 2, 3, or 4. And you have to choose exactly 1. Okay? That's what this rule is saying. Pick any x. For each x, there should be exactly one outgoing edge. The next one is dual. Pick y, then there should be exactly one incoming edge. You have to choose exactly one x that has an edge from x to y. Now if you have these things, you will see that the edges that you selected, which are denoted by this cycle x comma y, is this edge x comma y is in the Hamiltonian cycle. Okay? So if you have just this part, what will happen to the stable model? It will just generate all the possible selection of edges, where each node has exactly one incoming and one outgoing edge. Isn't this sufficient? Yes?
What is the definition of cycle?
Or Hamiltonian circuit. So here cycle x comma y denotes that the edge x comma y is in the Hamiltonian circuit. So in the last, you will see that cycle of 1 comma 2, cycle of 2 comma 3, cycle of 3 comma 4, cycle of 4 comma 5. That means 1 to 2, 2 to 3. These are the paths in the Hamiltonian circuit. Okay. Maybe let me show you first. I think I have to give a graph. So yeah, so this is actually what you will see at the end. Cycle predicate encodes the Hamiltonian circuit. So this means there's the Hamiltonian circuit goes like 1 to 4, 4 to 2, and 2 to 6, 6 to 5, 5 to 3, and 3 to 1. Okay, that's one Hamiltonian circuit. If you're interested in how many are there are actually 6 Hamiltonian circuit. Okay, so we will do that, and I'm not showing the whole program yet, so let's do one by one. So at this point, of course, all the Hamiltonian circuit will satisfy this requirement, right? But also some other assignment will be there too, right? Or other selection of edges will also satisfy this requirement, right? So what are those bad assignment?
You have to cover all the nodes, but here that does not satisfy that.
What do you mean by cover here?
Like you have to traverse through all the nodes.
Okay. What do you mean by traverse? Because computer doesn't know what you mean by traverse. Can you be more specific? Maybe even you can use the vocabulary that computers know here. So it knows node, edge, cycle. It doesn't know what you mean by traverse.
If there are n nodes, then in the cycles that we generate, all the nodes should be there in those cycles.
So if I have, let's say, this node, okay, if I have these, okay, if you select this, each node has exactly one incoming edge and one outgoing edge, and one incoming and one outgoing. That's fine, right? But this is a Hamiltonian circuit. No, why not? Because it's not reachable. So, yeah, but what do you mean by connected? So let's try to be more formal. So if you start from the one node, every node is reachable from this node. So now you have to define something called reachability, which you already did when you are doing the family relationship. You remember the ancestor relation? That's about the reachability. So what we do is we are going to define these things. Okay, maybe let's go with this. Reached y means that y is reached from the vertex 1, right? Because if you chose this edge 1, y, that is in the Hamiltonian circuit, then y is reached. Okay, so every step of length, every path of length 1 is covered here. And then you have to do the recursive case. So if x is reachable, or x is reached from vertex 1, and x and y is connected, or you can go from x to y, then you can reach y. Okay? Are we together?
So
Yes.
we are assuming we are starting from 1. We are assuming that we are starting from node 1.
Oh, node 1 is just an arbitrary selection. Yes, you can choose any node. It does not actually matter. But you have to select 1. Okay? Yeah. So here we happen to select 1. Yes. It does not matter if you change 1 with other numbers. Okay? All right. So that's the part. And this is actually neither choice rules nor constraint, because it has a single predicate in the head. Right? So other rules has this has choices, a curly brace, or the empty head, but this one doesn't have that. But it can be used for the definition, right? So you define the reachability. Okay. Okay. So we've defined the reachability, but we didn't use it yet. We have to use this definition. How can you use it? Now we're almost there. We need only one line to say that these are bad guys. So what should that be?
The word is 1 dot of n, they are not reachable.
1 dot dot n? No. You don't need 1 dot dot n here. How can you say this? Well, if you find at least one node that is not reachable, then this violates constraint. So just write this way. There is a y that is not reached, then this violates constraint. Right? This is the end. If you happen to worry about display, you can just add this line, and then Klingo will not show other predicate like node and edge. It will only show the cycle. Okay? All right. So typically, this is also called traveling salesman problem, and there are many variations. But one of the typical thing is actually finding optimal plan. So how can we do that? We are going to assign cost to the edges. So now the Hamiltonian circuit, there are actually 6 solutions for this problem, but not all of them actually optimal, because you can choose different paths to go there, right? And depending on the path, the cost of travel will be different, right? So here, if we want to go from 1 to 4 or 4 to 1, the cost is 1. But if you have 3 to 6, you cannot go from 3 to 6. You can go from 6 to 3. The cost is 3. Okay. So, what is the most optimal solution? And I can give you a quiz, and we can consume until the end of the class. But can you guess what will be the most optimal solution? What is the optimal plan? What is the cost for that plan? Maybe I should give some reward to those students who find the answer.
The width sum is
Hmm?
the width of the edge sum together to be minimum.
Yeah, they should. Yeah, that's exactly the problem is about. So it should be Hamiltonian circuit as well as it should have minimal cost when you add up all the costs assigned to the edges. Okay. 9. Okay. How can we do?
1 to 4.
So 1 to 4, 2, 5, 6. Oh no. Okay. All right. Well, let's not waste time on this. Let's just show directly what is the solution look like. Now we have to now introduce the cost, and the way that we do is very simple. You have a new predicate cost, okay, and you just need to say from edge 1 to 2, the cost is 2. Okay, so you can just encode it. No surprise. Now finding the optimal plan is easy. Just write this one line, and it will find the solution. Okay. So what does it do here? It will try to find the pairs C, X, Y, and here this is like the cardinality constraint, but we want to actually minimize the cost here. So finding all passes in the Hamiltonian circuit. Okay. So if you so let's say this part is to be appended to the program that I showed before. So what will happen is it will compute all the costs. It will actually add up all the costs and find return the minimal cost plan. Okay, we'll actually talk a bit more about this later when we go into the aggregate part. So the syntax may not be yet familiar, but there is actually the general concept of aggregate that we'll talk maybe next time. But let me just show you what happens here. So let me show you the code first. So this is Hamiltonian circuit code, and this is a graph that I showed. Right, okay. This is optimized statement, and this is cost. So all I need to do is just to give everything. So Hamiltonian circuit, graph 3, and edge cost, and optimize. Okay, so the solution is this one. The minimal cost is 11. Okay, so 1 to 2, and then 2 to 5, 5 to 6, 6 to 3, and 3 to 4, and 4 to 1. That's the minimal plan. Now Klingo actually shows other plans too, which is suboptimal yet. So what it does is it tries to find one and try to optimize it. If you can find a better plan, it will produce, and so on and on until the optimum is found. Okay, that's what Klingo is doing. Ooh. Right. Okay. There's one thing here. Okay, let's go into the Sudoku. So what is a Sudoku? You have to so you have to place numbers from 1 to 9. Okay, so that no two numbers in 1 to 9. Okay. No numbers are repeated in the same row or column or same 3 by 3 box. Right? Have you played this? Okay. Good. So in a sense, this is similar to N-Queen's puzzle. So this is actually the solution. So the last problem in the handout is actually using the about the Sudoku puzzle. So let me try to get into that. Okay, so 9 by 9 may be too much time consuming to do, but we can do 6 by 6, right? So let's try. Usually in the Sudoku puzzle, there is only one solutions, okay? People don't like having Sudoku puzzle with more than one solution, okay? All right, so let's play together. What should we do? So tell me the coordinate and maybe the number. That will be easy to do.
1, 1 is 2.
1, 1 must be 2. Huh.
That's above the 3 and next to the 4 plus the 4.
So yes, 1. Okay, let me give the row number and the column number. So Pema is saying this should be 2. Why?
Because if you look at the, well, 2 is not going to violate the vertical column, and 2 is not going to violate the right-hand column.
So basically, you just look at the rows or columns that has most numbers, right? Now, if you look at the first row, according to the first row, it could be either 2 or 3, right? But if you have 3, then it will violate the column constraint. So it will be 2. So it should be 2. Okay, that's good. What else should we do? Well, let's do easy one first.
1, 6.
Because 1, 6 is now easy because you have 2, then this must be 3. Right? Okay, good. What else?
3, 1,
3, 1 is also easy, yes. What should be? 4. Good. And what is next easy one? 3, 3, right? That should be 3. Good.
6, 2.
4, 2, or 6.
Okay, let's do turn by turn. So let's start with the last row over there and come back and maybe go this way. Okay, anyone in the last row? What should be the next easy one to use? 4, 2, because now they're all 5 numbers filled. What should be the number here? 6, okay. The row above, before? Now 4, 6 is also easy. So what should be the number? 5. Okay, good. Okay, and then the second row here.
2, 2 should be 1.
2, 2 should be 1.
Yes.
Haha, why?
Because 6 is in 4, 2. And that would mean
So-
by process elimination it should be 1.
Okay, let's say this must be 1. And what was your other thing that you?
It could be, the other possibility is 6, but 6
Okay.
is in 4, 2.
I see. So it could be either 1 or 6 if you look at the first box, right? But if you put 6, then it will violate. Okay? So 6 is not, so it must be 1. Okay? It becomes easier for you guys.
2, 3 would be 6.
2, 3 will be 6. Okay. Last row over there.
6, 3 should be 1.
6, what?
6, 3 should be 1.
6, 3 should be 1.
Yes.
Why?
Because 5, 3, the row 5 already has 1.
So this is, according to the row, column 3, there should be 2 numbers that are missing, right? 1 and 4. Right? So why not 4 here? How do you know that it should be 1? Ah, that's actually, you're looking at this guy. Okay, so maybe, yeah, okay, that's fine. So if we put 1, then this is a problem. So instead of this one, maybe we should look at this guy first, right? So here again, you have 2 choices. If you just look at the column constraint, that's 1 and 4, 1 and 4, right? If you just look at the column constraint. But if you put, you cannot put 1 here, so by looking at this, because 1 is already here, this should be 4. And then it becomes 1. Okay, so 2 steps there. Okay, good. So, okay. You guys.
2 should be 3.
5. Yeah, so that's the easy one. Yeah, that should be 3. Okay, becomes easier for you too, right?
6 should be 2.
2. Okay, good. Right, now we have a bit more difficult part here. More symmetric here. Let's go. Okay, all together. So what should we do here? 2, 5. 2, 5 should be 5. So what's the reason?
It should either be 3 or 5 in that.
Oh, you're not in the section. Okay, but anyway. So if you look at the column 5, there are actually 2 numbers missing. So that's a 5 and what? 3. But 3 is actually, if you look at the this guy, 3 is already there. So 3 is not possible. So then it's 5. And then it becomes easy to do. Okay, I'm going to fill the rest of the thing. So we are done. Okay? All right. So that's the solution that we know. How do we solve this Sudoku in Klingo? And I have 9 minutes left, so I think I can finish this. You'll get lost probably. Okay. So numbers 1 through 9. Okay, so this is easy. And I'm going to show you these rules, and you try to read it in English. What does this rule do? So let me give you the reading for this predicate. So A, R, C, N means the row number R. So R and C and N can range from 1 to 9. So row number R, column number C, there should be the digit N there. Okay? So 1, 3 means the position 1, 1, there's a number 3 there. Okay? So what does this rule doing? What is this rule doing? It is assignment, yes. What is the domain here?
Is the coordinate.
Row and column, yes. There's a domain, and what is the range? Number. So what you get is, if you write this, what are the stable models?
1 will be 1 to 9.
Yeah, you just put each position, you fill each position with a number. Okay? So if you're very lucky, you already have the solution. Okay? Actually, I should say that you have to also encode the instance. So for this kind of thing, you can give a data which is 119 and say 1, 2, 3, 4, 5, 5, 8. So actually, I have to give this data instance. Assuming that's already given, so we are trying to do it. We are trying to write rules for that. Okay. So this one is simply put the numbers in each of these coordinates. So choose one number for each row and each column. That's what it's doing. What about this guy? So this is almost similar to the first one, but now C and N is fixed. That's a global variable, and you have to choose exactly one row. So, I mean, basically you just change the comment here. So choose one row for each column and each number. If you're given a column and number, you have to have exactly one row for that. And similarly for this guy, okay, so if you are given a row and number, there should be exactly one column. So basically you have 3 things. If you're given the 2, that should uniquely determine the other one. Okay, you're given the row and column, then you should give the number, row and number, you should give exactly one column and also the other one. That's what it's doing. So until this part, what do you get? You will get all the numbers are filled into the grid, and you will see that no numbers are repeated in the same row or column. There's actually one more requirement here, which is the box requirement. And the box requirement can be actually represented in different ways, but this is actually some complex equation. What is it doing here? What is this thing? Can you guess?
The first one will be down to the cell.
Mm-hmm.
And with empty, we will give each box the ID or something.
Exactly. So the function here, so r1 minus divided by r comma times 3 plus c minus 1 divided by 3. This gives the uniform number for each box. Okay, that might be a bit difficult, but let's actually try to do something here. So if I have, okay, 1, 2, 3, 4, 5, 6, 7, 9. Let's say 1, comma 7, position 1, comma 7, and 3, comma 8 are in the same box, right? Right? They're in the same box. So what is the value for this? What is R1? So let's actually plug in it. So if R equals 1 and C equals 7, what is this value?
2.
Okay, you're fast. So let's do slowly. So if R equals 1, so 1 minus 1 is 0. So this is all 0. And 7 minus 1 is 6. 6 divided by 3 as an integer is 2. So this number becomes 2. Now R1 is 3 and C1 is 8. So then what should it be? So R1 is 3 minus 1 is 2. 2 divided by 3 is an integer division, so it's 0. 0 times 3 is still 0. And C1 minus 1, so it's a 7 divided by 3. The integer part is 2, so this is again 2. Okay? So roughly every position here will have the number 2, according to this equation. And I believe this is actually all 0, and this is 1, and maybe 3, 4, 5, 6, 7, 8. Okay? So any numbers that belong to the same box will have the same value for this function, so that you can say that if they are in the same box, then this value is constrained. Now, a few years ago, I gave this as a homework problem, and students' solutions are very diverse. So actually, most diverse part is actually how to represent this 3 by 3 box constraint. Okay, so. All right, so something that I want to emphasize, okay, these are the instances that I said, is about the elaboration tolerance. So this was what John McCarthy said in 2003. He's one of the founders of AI, and he said, a formalism is elaboration tolerant if it is convenient to modify a set of facts expressed in the formalism to take into account new phenomena or changing circumstances. Actually, let me go through this maybe next time in more detail, but next time what we are going to do is we are going to solve variations of this Sudoku puzzle. There is actually offset Sudoku puzzle where you see that in addition to the original problem, you have the colored regions here. So this forms another constraint. Okay, we'll solve this puzzle. Anti-nice Sudoku puzzle. So okay, actually, I'm going to say that next time. So there are quite a few variations of Sudoku puzzle, and each of them can be solved in just adding a few more lines to the program that I showed you. And for the killer Sudoku, this is really killing you, maybe, but if you know how to represent those constraints, it is actually not very difficult puzzle. Okay? All right, so we'll continue this next time. Any question? Okay, so then let me open the exit ticket.